In this video, we're going to take a look at the concept of a linear combination. And on the surface, when you really look at what a linear combination is, it seems very simple, but it has a lot of deep consequences to it. And what this topic will allow us to do is to look at a linear system in, again, a slightly different way, right? So it's really amazing how just looking at a linear system in different ways can lead to these, different concepts. Very, very important. All right, so to give you an idea, let's start with a specific example. So let's say we have the system 2x plus y is equal to 1, and then let's say x minus y is equal to 4, right? Really simple system, and we have so many different ways that we can solve this now. But we've looked at this system in different ways, so we have an augmented form of a system. So our augmented system of this one is basically, we don't really do anything major to it. We just keep all the relevant information like this, and then we solve. Then there's the matrix form, right? So we have our matrix form, and in that matrix form, what we do, we represent the coefficients in their own matrix, so 2, 1, 1, negative 1. We don't throw away our variables, we keep our variables, the x, y, and then we keep the constants over here, right? So this form led us to the important concept of echelon forms and pivots, and just looking at it, and the concept of rank and nullity, all those ideas came from this. From this form, we developed the idea of the inverse of a matrix, right? And all the properties of the inverse. And then when your coefficient matrix is square, we can say more about the inverse by looking at the determinant, right? So the matrix form led us to those concepts. Now it turns out there is a vector form that this system can be represented as, and this is how it works. For instance, if I look at the columns now, right? So for instance, I have a column here, my first column, that's associated with the variable x. Then I have a second column here that's associated with the variable y. And then I have a third column here that's with my constants. So this system, for instance, could be written like this, right? If I make sure that all my columns have the same dimension, so I could put 2x and x there and call that a column. And then what I'm going to do is I'm going to put a plus sign there and then add the other column, which has the positive y and then the negative y, and then keep my equal sign, and then a third column that has my constants, right? Okay, so now we can see this is equivalent, right? Because we know how to add vectors. We add them the same way we add matrices. We would add the corresponding entries here, add these corresponding entries, and then to get our equations, we would just equate them to the corresponding entries on the right-hand side, right? So nothing major there. But now, let's do the reverse of scalar multiplication. In scalar multiplication, we normally, distribute our constants. Well, if I look at this vector, both components have a factor of x. So what if we factored out the x? Well, that would leave me with a constant vector 2, 1, right? And what if we did the same thing with this second column? What if we factored out the y? So take the y out, and then that leaves 1, negative 1. And then here we have our constant vector 1, 4, right? So basically, finding the solution to this system, right, is equivalent to finding the scalars such that when I multiply this vector by the scalar x and then add to that the product of this vector and this scalar, I want to get this vector as my solution. So in other words, I want to find these scalars so that when I perform the operations on the left, I will get the vector that's on the right. All right, well, let's see if we can actually find those scalars, right? So in order to do that, we would have to solve the system, right? So again, we have lots of different ways we can solve it. I am just going to solve it using, again, very basic methods. If I add these two equations, so if I add them, I'm going to have 3x, right? And then 0y, and then that's equal to 5. So then x is 5/3. And then plugging my x equals 5/3 back, let's say we plug it into the top equation. So then I will have 10/3 plus y is equal to 1. And then my y will be negative 7/3. Right? So let's actually test it now and see if this vector form, right? And we're going to write this down in a second. This vector form is satisfied using these scalars. So now let's check this to see if it works, right? So let's check. So if I take my 5/3 and multiply the vector 2, 1, and then take my constant negative 7/3 and multiply the vector 1, negative 1, well, let's see what we get. So distribute the 5/3, that gives us 10/3 and 5/3 for the first vector. Distribute the negative 7/3, and what do we get? So that's going to give us a negative 7/3 and then a positive 7/3. And then let's do our vector addition. So if we have 10/3 plus negative 7/3, that is 3/3. And then 5/3 plus 7/3, that's 12/3. And there is what we would expect the 1 for. So it does work, right? So this form of our linear system now, because we're using vectors to represent it, you can refer to this as a vector equation, or this is the vector form of my linear system. So let's write that down in a more general sense, right? So in general, and remember again, way back when, if we can remember back that far, when we wrote down our linear system for the very first time. So, and if you remember, that was an m by n, and that's what I'm going to do right here. So let's do dot 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 and then plus a 1n x to the n, and then we have b1, and then a 2,1 x1 plus a 2,2 x2 plus dot 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 a2n xn, that's equal to b2, and then we go down until we have m rows. So I'm not even saying that it has to be a square like an n equations, n variables. It could be m equations, n variables. So m1 x1, and then a m2 x2, going all the way across to a m n xn, and then that will be equal to bm, right? So this was our general linear system. So now for this particular system, we have the equivalent vector equation, right? So we have the equivalent vector equation. Well, what does it look like? Well, we basically look at now the columns. So like the first column here, they all have an x1 in common. So we would factor out that x1 and just take the first column of A's and make a vector out of it. So A11, A21, dot, 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 AM1. And then do the same thing for the second column. They all have an x2 in common. So factor out that x2 and keep the entries that are in the second column. So A12, A22, dot, 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 AM2. And we continue this until we get to the last column with their variables. So in the last column with the variables, we'll have an xn in common. Factor that out. What are we left with? A1n, A2n, dot, 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 AMN. And then keep our equal sign, and then make another vector with our constants on the right. So B1, B2, dot, 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 BM. Right? So these are now, so now this same system has another way of being represented, but now using vectors. So let's rename these. So if you notice, each of these columns, they have m components, right? Starting from the 1 going all the way down to m. So these are vectors in Rm, right? M-dimensional Euclidean space. I'm going to call this column V1. I'm going to call this column V2, right? Dot, dot, dot. This is going to be Vn, right? And then this I'm just going to call B. But now again, I'm going to use that vector notation. So therefore, our system can be written as x1 times v1 plus x2 times v2 plus dot, 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 xn times vn, and that's equal to the vector b. Right? Now, this expression, so let's write it, let's state everything here. So the xi's, those are your scalars. In other words, those are the constants that we're trying to find that I would need to multiply the respective columns by, and then when I add them together, if I find a solution, right, then I would have to get the column of b's, right? So the xi's, these are your scalars. And then the vi's, those are vectors in Rm, as is b as well. So I should put, in fact, let me just put it here. And then b is also a vector in Rm, right? This expression on the left-hand side, where we have vectors and they're all being multiplied by their respective scalars, this expression is what we refer to as a linear combination of the vectors v1, v2, vn, right? So and notice this can be written with the sigma form. So the sigma form of this, let's say k going from 1 to n, it would be xk times vk, and then that will be equal to b. So this expression here, which I just have expanded in the line above, this is what we define or call a linear combination of a set of vectors v1, v2, dot, 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 vn. Right? So let's write that down. So the expression my summation, k going from 1 to n of xk times the vector vk. So this expression is called a linear combination, right, of the vectors v1 through vn, right? So of the vectors v1, v2, dot, 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 vn, right? And so basically, a linear combination is where you are allowed to do two basic operations. You are allowed to scale each vector by its own constant, and then you're allowed to add those products together. So a linear combination consists of two of the most basic vector operations: scalar multiplication and vector addition, right? Which is the same as matrix addition, right? So these are the two operations that you're allowed to do in a linear combination. And if you think back to the way we defined a linear equation to begin with, that's exactly what it was. All we were allowed to do with our variables, right? We can multiply them by constants, and we can add them and add those products together. Same rules, but now in this seemingly more, kind of sophisticated setup, right? And not only that, but remember, this came from a linear system. So what would it mean? Like one of our fundamental questions about a linear system is, when does it have a solution, right? When does it have a unique solution? Well, in terms of a system being consistent, it would mean that I would have the ability to find these scalars, the x1, the x2, the xn, so that when I form this linear combination of these columns, then I will be able to produce the vector b, right? So the concept of a consistent linear system can now be rephrased with the language of linear combinations. So our linear system is consistent, right, if and only if the vector b can be written as a linear combination of these n vectors. So if and only if b can be written as a linear combination, linear combo, right? Linear combination of my vectors. And again, these vectors, they just make up the column in my coefficient matrix. So the v1, v2, dot, 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 vn, right? So again, it's like we're still solving the same old linear system problem, but now just looking at it through the lens of vectors, we get a completely different way of formulating this question. All right, so let's see if we can do a particular problem, but now have the problem be phrased with this terminology, right? So let's look at an example. And here is the question. So we are going to determine if the vector, let me write down this vector, so it's negative 1, 1, 10. So if this vector may be written as a linear combination of these three vectors, 1, 0, 1, -2, 3, -2, and let me scroll down, -6, and let's make this a 7 and that a 5, right? So again, look at this particular wording. It says, first of all, we don't see any equations per se. We don't see any variables. All we see, we're given four vectors, and we're asked to determine if this vector can be written as a linear combination of these three vectors, right? And obviously these are three-dimensional vectors. So these are vectors that would have components x, y, z, and it's not completely obvious if the answer is yes or no, and that's why we're going to try to figure it out, right? So let's formulate this using the definition we just came up with. So the linear combination is of these three vectors. So that means I am trying to find constants. You can use x1, x2, x3. Many times they would use c1, c2, c3 for constants that would multiply these three vectors respectively, and we would want to get this vector as an answer, right? So let's use the c's for our scalars. So let c1, c2, c3 be our constants. And what this question is asking us to do is to see if we can find constants such that c1 times my vector 1, 0, 1 plus c2 times my vector -2, 3, -2 plus a constant times my third vector -6, 7, 5. If I can find scalars where I perform this linear combination and I get this vector -1, 1, and 10, right? If we can find scalars that would satisfy this, then yes, the answer to this question is this vector can be written as a linear combination of these three. If we can reach the conclusion that they aren't constants, c1, c2, c3, that would satisfy this vector equation, then the answer would be no. This vector -1, 1, 10 cannot be expressed as a linear combination of these three columns. All right? Well, how do we know for sure? Well, what we do is we turn this back into a linear system, right? And again, this is how it would work. So let's say we perform the operations on the left. So if I distribute the C1, the first column becomes C1, 0, C1. If I distribute the C2, the second column becomes -2, C2, 3, C2, -2, C2. If I distribute the C3, the third column on the left becomes -6, C3, 7, C3, 5, C3. And then I still have my single column on the right. So -1, 1, 10. Well, again, if I perform my operations of vector addition, I would add the corresponding entries or the corresponding components, right? So it looks like this. Now I can write a single vector on the left. I would have C1 -2 C2 -6 C3, and then I would have the 0 there, which I won't write, And then I would have a 3C2 and then a plus 7C3. So 3C2 plus 7C3. And then the third row is now C1 minus 2C2 plus 5C3. And again, what I want to get, what I want my constant or my vector to turn out to be is -1, 1, 10. And again, when you think of these as matrices, I have a 3 by 1 on the left, I have a 3 by 1 on the right, and we're saying that they're equal. So that means, again, this has to be equal to that. And then my middle component here has to be equal to my middle component here. And then my third component here has to be equal to my third component here. That's how it converts back into a linear system, right? And then we have to think, well, how are we going to solve this? Well, I don't know about you. I am always a little partial to some good old Gaussian elimination. So what I'm going to do is to convert this to the augmented form, right? So let's do the augmented system. And then that means now just looking at the coefficients here and including my constants on the right, then our augmented form is 1, -2, -6, -1. And then I have my 0, 3, 7, 1. And then 1, -2, 5, 10. And then, yeah, let's try to solve this, because if we can solve it, if we can find at least one solution, so if this linear system is now consistent, then we can answer in the affirmative and say, yes, my vector, let me scroll back up just a little bit, my vector -1, 1, 10 can be written as a linear combination of these three vectors, right? All right, so let's see. We have the 1 in our pivot position, so that's fine. We already have a 0 there, so we just need to eliminate this 1. So let's take negative row 1 added to row 3. It's really interesting that, after, so much time, we're still working through solving problems using Gaussian elimination. Amazing. So 0, 3, 7, 1. So now take the negative of row 1, add it to row 3. Let's see what we have. So that will be a 0. And look, we also eliminate this. So this is 0. And then we have the negative of this. So that's 6 plus 5. So that's 11. And then the negative of this is a positive 1 plus 10. That's 11. And it's really nice. It's helpful, the fact that with one row operation we have a triangular form, right? Now remember, all we have to do is determine if there is a solution. And we can tell that this system will have a unique solution. Why? Well, because every row, right, has a pivot, or I should say a non-leading entry. We haven't made them formal pivots yet. In fact, I'm not going to. What I'm going to do is just use back substitution and figure out what these constants would be, right? So we know that we will have a solution. So we can answer the question in the affirmative right now, but I want to find the constants just to verify that, again, they do work, right? So from this equation, I have that 11C3 is equal to 11. So then C3 is 1. And then this the middle equation now tells me that 3C2 plus 7 is equal to 1. So 3C2 is -6. So C2 would have to be -2. And then the top equation tells me that C1 plus 4 minus 6 is equal to negative 1. So that's a negative 2, so add that over. So C1 would have to be 1 as well, right? So again, let's answer the question. So yes, my column negative 1, 1, 10. And notice they're still right here. You notice those columns, they're still there, the 1, 0, 1, the negative 2, 3, negative 2, and the negative 6, 7, 5. These are the columns that we started with. So yes, this column may be written as a linear combination of, again, those three columns. So 1, 0, 1, negative 2, 3, negative 2, and negative 6, 7, 5, right? And the reason why is because we ended up with a consistent linear system. How would you check this? Well, do exactly what the linear combination says to do. So here's our check or verification. If I take C1 and multiply the first column, so if I take 1 times 1, 0, 1, and then add to that C2 times the second column, so negative 2 times negative 2, 3, negative 2, and then plus the third constant C3 times my third column, so 1 times, where are we? Negative 6, 7, and 5. Well, we would expect to get the negative 1, here it is, negative 1, 1, 10. So let's see. So we have, in the first component, we have 1 plus 4 minus 6. The middle component, we have 0 minus 6 plus 7. And then in the third component, we have 1 plus 4 plus 5. So 1 plus 4 plus 5. And where is the drum roll? Where is the confetti? Something. So we got negative 1 and 1 and our 10, right? So it does work, right? And again, it's on the surface, it's such a simple idea, but this idea of taking one thing, in this case a vector, and writing it as a linear combination of a bunch of other things is such a fundamental principle in a lot of areas. And I'm not just talking about, theoretical math. I'm talking about applied sciences, engineering, computer sciences. This concept of a linear combination is fundamental. And now you've been exposed to it. So think about it, and we'll definitely work on more examples, but hopefully you understand exactly what this concept is all about. Right? And I'll see you in the next video.